last of our conic sections that we're going to take a look at is a shape that we're actually familiar with from our study of them in the context of functions, is the parabola. And so you can see there it's the result of a plane intersecting with a cone where the plane is parallel to the slant height of the cone. And so therefore we'll never hit that bottom cone, so we end up with just one shape rather than two branches like we saw on the hyperbola. And it is the same type of parabola that we had studied previously. We're just going to look at it from a different context. So we're going to look at the rule that defines it, that establishes it, and these kind of new features, these new elements of the shape related to some of the others that we've looked at, with some overlap with things that we've looked at before. So if we move along, we can see again, we can have a parabola that can open either in the vertical direction, as we see here on the left, and so that's when we're going to see the x squared in our equation, as opposed to a parabola that opens in the horizontal direction, something that we never saw before, because if something's a function, it's going to pass the vertical line test, but a sideways parabola will fail the vertical line test. So we're not looking at these as functions, we're looking at them as these conic sections, these cross sections. And so it's going to be sideways if it's the y squared in the equation. So notice the other variable is not squared, and that's what we experience with just a regular equation of a parabola, like y equals x squared, or if there's more stuff going on, it was still always only the x variable that's being squared, with the y variable just being to the first power. So here we can see that whichever variable is squared dictates the orientation of the parabola. So the parabola is going to either open up or it could be down, as we'll see in some of our examples. If the x is squared, the parabola is going to open to the left or to the right if the y is squared. Now, just like we've defined our other conic sections with a rule, we do that here with the parabola. So the points that are on the curve of the parabola, so take any old point like that, x, y, and so those are points that are equidistant, so the same distance from two features. So one of those features is called a directrix, and so that's this line right here. So it's just a horizontal line, or if the parabola is opening sideways, it's a vertical line on the opposite side of the curve of the parabola. So the parabola will never intersect with the directrix. It's always on the opposite side. So the points on the parabola are the same distance. They're equidistant from this directrix line and from a focus point. And so the idea being that this distance and this distance are equal to each other. Now if I pick a new point that's somewhere, let's say over here, this distance and this distance are equal to each other. So this perpendicular distance, straight line distance to there. So you can see that depending on where the point is along the curve of the parabola, those two distances will be different, but they'll be equal to each other. So the farther out we go in the parabola, so if we go way out here, both these distances are going to be really large, but again, those two distances would be equal to each other. They would be the same distance. Now, if we look at the equation, we've got one variable that's squared, that's our x squared or our y squared, the other one is not. We've got hk is the vertex of the parabola, and that's the same as what we had studied previously. So that's just either the lowest point or the highest point of the parabola, or the left-handmost or the right-handmost point if it's opening sideways. So the vertex is going to be that hk. So now instead of hk being the center of the shape like it was for the other three conic sections, it's now the vertex of the shape. And then we see this 4p that shows up in the equation. So when the equation is written in this format, with the x squared, the squared variable isolated on one side, and then the other variable piled up on the other side, we're basically going to have a number that's going to be on the outside of a set of parentheses, multiplying the non-squared variable. So y minus k or x minus h, as it is in the second example over here. And so that number that's out in front, its value is 4 times this number p. And what p is is the distance from the vertex to the focus. So this distance right here, from here to here, that's P. The distance from here to here, that's P. So whatever number we have undistributed out in front of the variable on the opposite side of the squared variable side of the equation, that number is 4 times whatever that distance is, that number P. And so we're going to use that number P to figure out what the location of the focus is, and we're going to use it to locate the directrix, because then we're just going to move the opposite direction that same distance, so just negative P units. We're going to move to figure out where the directrix is located. So if that 4P number, if the number in that position in the equation is 20, you take that number, set it equal to 4P. If we then divide both sides by 4, we get P equals 5. So that means the focus for that parabola is going to be 5 units away from the vertex. And then the directrix is going to be the opposite of that. It's going to be negative 5 units away. And so P could turn out to be a positive or a negative number. It could be either one. If it's positive, then that means we're going to be going up or to the right from our vertex. If P was negative, we'd be going down or to the left from the vertex. And then, of course, the directrix is just going to open, or is going to be the opposite direction from the vertex. And again, the focus is always on the inside of the curve of the parabola. The directrix is always on the outside of the curve of the parabola. So I know, again, as with all these shapes, we've got lots of new terminology and features that we have to find. In the next video, we'll take a look at a few graphing examples to see how all this fits together.